introduction and thanks for having me. I was told that I can tell people ahead of time to just ask questions as I speak. I find that a better model than me talking for a long time and then, you asking me questions about the first slide an hour later. So just, if you want to ask a question, raise your hand. I'm trying to be as perceptive as I can, and then we can just handle questions as they come. If the discussion ends up being so in-depth that I won't get to my last slide, I'm not going to be angry about it either. So, I'm really interested in how people learn with visuals, and I've become increasingly interested in this idea that visuals are intuitive, because sometimes they are, sometimes they're not. And I feel like when we teach, we often assume that models like these are just really intuitive because they show things or make intuitively accessible things about molecules that we would otherwise not see. And I feel like in many of the areas in our life, visuals are actually very intuitive and we don't think about them. Like we stop at red without having to think about it, or we use emojis because they're making intuitively accessible the tone that we want to convey in text messages, and we do napkin drawings. I'll actually talk about these results later on one of my later slides if I'll get to them. But we use visuals with the assumption that they make things intuitively accessible, and that is how I came to start my research. I actually started out not doing research on chemistry, but on fractions learning, and visual representations like these are widely used in instruction on fractions. So we might show students circles and rectangles and sets and number lines, depending on what scenario about fractions we're talking about, fractions as like sharing pizzas or sharing chocolates or M&Ms. For some reason, these are always about food. But we assume that they help students think about fractions, and that's why we provide them in addition to like text scenarios and symbolic fractions. And I was wondering when I started out doing my research whether students actually benefit from seeing all these different kinds of representations and whether they really make it easier for students to learn. At the time, there was actually no experimental evidence that multiple visual representations in addition to text and symbols is actually better than just using one visual representation. Like, what if we always use number lines or always pie charts? So I wanted to do that experiment to compare learning with a single visual or multiple visuals when students learn about fractions. So I was also interested in whether students need additional support in connecting the visuals to the symbols, because we know that for visuals to be effective, students have to connect them to the other symbolic or textual representations that students encounter. And we also know that students may not do that spontaneously. So in this experiment, this was actually my very first experiment, the one that I did when I came to the US for just that summer internship that then made me stick with academia and the United States. So it was basically a 2x2 factorial experiment where I compared single visuals to multiple visuals, and then prompts that asked students to self-explain how the visuals show information that we normally see in fraction symbols, and another group factor where students didn't get those prompts. So what I found in this experiment is really what made me choose this for a career. I found that, so you see on the y-axis here, I should say first, performance on a delayed post-test. So in this experiment, it was students in elementary school fractions classrooms receiving a pre-test. Then they worked with an educational technology that where the version that they used corresponded to these 4 experimental conditions that I showed on the previous slide, and then they got a post-test, and then we came back a week later for a delayed post-test. I think the delayed post-test is most meaningful because it kind of tells us what sticks. We had the test that you're seeing here is composed of reproduction as well as transfer items. So we see here that students who get multiple visual representations without prompts to connect the visuals to the symbols, they actually showed the lowest learning gains. Students who received multiple visuals with the prompts to connect the visuals to the symbols, they showed the highest learning gains. The reason why I find that so interesting is that this is actually common practice. This is what you see in most textbooks, and it actually corresponds to this idea that we view visuals as being intuitively accessible. Like, why do I need to explain to students what a pie chart means? Like, it's obvious, isn't it? Well, it's not. And if we don't help students make these connections, then they're not going to get the most out of the visual representations. We'd be better off giving them just one representation. By contrast, if we support students in interpreting the visuals, that's when students get a benefit out of them. Yeah?
I was just wondering, for the single versus multiple representations, was the multiple, like on your previous slides visual, where it's literally multiple within a single question, or was it multiple spread out across the questions?
I've done both. So in this specific experiment, it was just one visual per problem, but multiple across different problems. But I've done experiments with multiple within the same problem too. Yep. Good question. All right, so that's how I started out my career. I was then interested in, well, what is so difficult about learning with visuals? Because only if we know what makes it difficult for students can we help them navigate multiple visuals. So, and thinking about this, there are really a lot of things that we expect students to do when we present visuals to them. So, first of all, what I mean when I say a visual representation is really an object that has some similarity-based mapping to the referent being some concept that they are learning about. Concepts, I think, well, the way I'm using the term is some generalizable mental representation of a phenomenon. For example, that ice floats in water, I would say, is a concept. And Lewis structures and ball and stick models are visual representations of water. So in chemistry, we may use these kinds of visuals to explain why ice floats in water. And students actually have to learn a lot of things about the visuals to make sense of how they're showing the concepts. Like, they have to learn that the red sphere stands for oxygen, that the ball and stick model doesn't show electrons, that the Lewis structure shows electrons, which are shown as dots. And these dots or the electrons explain why, when you have multiple water molecules, they are attracted to one another in this way, so that when ice forms, they actually form these lattices, or, well, they're not lattices, sorry. They form these structures that are less densely packed than when water is liquid, and that explains why ice is less dense than liquid water, and that explains why ice floats. So it's actually not surprising to me that this being fairly complex leaves many students confused about how they can use these visuals to make sense of complex phenomena like ice floats in water. Because first of all, they don't necessarily know starting out like how the visuals show water, and they also don't really know what water is. So they have to learn what I call visual skills, like knowledge about how the visuals show information at the same time as they're learning about the concepts that make up the domain knowledge, right? And they do that in some iterative fashion because they're learning about the visuals at the same time as they're learning about the concepts, because only when they've learned enough about the concepts can they actually see how the visuals show the concepts. So this must happen in some iterative fashion. And what I'm interested in is how we can use educational technologies to support students throughout this iterative process. So why do I think educational technologies can help us with this? Well, for one thing, in many domains, including chemistry, students actually learn the domain knowledge by solving problems where they have to manipulate the visuals or construct or modify visuals to solve the problems. So if we give students interactive visuals within an educational technology, we can use the information that we get from students manipulating the visuals to infer what knowledge they have about the visuals, and that allows us to diagnose in real time the individual students' knowledge about not just the content but also about the visuals, and that allows us to give adaptive support for students in this iterative process about learning about the visuals and the concept at the same time, and ideally that would help them learn not just the domain knowledge but also the visual skills. So that's the idea or the problem that I'm trying to solve with my research. Now the perspective that I take on this is really, what we do in the learning sciences. We have some theories about how people learn, and then we develop educational technologies that help students learn, and then we do experiments with these. I like to do in vivo experiments, so experiments that are done like as part of regular instruction. And then through that we can, it's really, like, I go through many iterations of this in kind of a design-based research process. So as I'm conducting experiments, I get data about, that help me build theory about how people learn, which then helps me refine educational technologies, which then, help me collect more data and kind of go through this cycle to close the loop really between learning theory, educational interventions, and experimentation. The idea being that all together that will help me improve learning with visuals. So this is also the outline of my talk, and specifically I'm going to focus today on 3 questions related to each of these areas. First of all, what are the visual skills that students need to learn to better learn the domain knowledge? Then second, how do we design educational technologies that support students' learning of these visual skills? And then how should we use these supports in real educational environments to best enhance students' learning of the domain knowledge? Let's start talking about the visual skills first. In my mind, the visual skills that students need are really specific to the given domain and the types of visuals that are being used in that domain to illustrate the concepts that are being covered. So when I started out doing research in chemistry, really my first step was I didn't want to assume that I knew what those visual skills necessarily were. I developed something that I like to call a domain grounding framework. So the idea is to combine top-down and bottom-up methods to really uncover what visual students use to learn concepts and what skills they need to learn to make use of these visuals to learn concepts. And I identified 2 qualitatively different types of visual skills. So one of them I like to think of being more analytical, and the other one is more intuitive. So to uncover these visual skills, I started out by just reviewing instructional materials that are being used in chemistry courses. I focused this on introductory level chemistry courses. So I looked at textbooks, I looked at online resources, I looked at lectures. I also interviewed instructors, so PhD students as well as chemistry professors or lecturers. And then once I identified which visuals were being used to focus on which types of concepts, I then looked at what skills students needed to use these visuals to learn about the concepts. And to do that, I conducted more observational studies where I looked at students actually solving chemistry problems with those visuals. I conducted interviews with the students and think-alouds while they were solving these problems. I also interviewed experts, so PhD students or chemistry instructors. And in the end, I did something like a cognitive task analysis, which told me, well, these seem to be the skills that students need in order to make sense of this concept, kind of similar to what I illustrated on that slide with ice floats in water. But then not all of those visual skills are actually a stumbling block to students learning of the domain knowledge, right? Like some skills might actually be intuitive, or students might already have them from like high school chemistry. So to find out which of these skills are actually difficult for students, I again conducted observational studies and interviews and think-alouds with students and experts. So what I did there was I compared how students were using the visuals and how experts were using the visuals to see what's the mismatch, like what are the things that students do that students don't do that experts do, and that gave me a sense of, well, what do students need in order to get to the more expert level. So this led me to this taxonomy of more analytical versus intuitive skills. So I want to illustrate that with a few examples. So the analytical skills set that I'm going to focus on are sense-making skills. So verbally making sense of how different visuals show concepts. And I brought in a video that I'm going to show you from, so let's see if this works, from a chemistry lecture by John Moore. So he's a chemistry professor at UW-Madison, and here he's using ball and stick models and Lewis structures to introduce ideas related to bonding. And we weren't able to get the audio hook up to the HDMI, but I think these speakers are loud enough. So I hope this will work. It's a 3-minute video, and I'll just play it for you right now.
Now, when we draw it on paper, we don't show the three-dimensional structure. Sometimes we do, but this kind of drawing that I made here does not show it. What it does show is a projection of that structure onto a plane. So if I hold this three-dimensional structure up like this, and just take each atom and project it perpendicular onto the chalkboard, then I get this diagram that I showed here. Sometimes we'll make a diagram where we try to actually draw it in 3 dimensions. One way to do this is to use like a wedge for an atom that's out in front of the chalkboard. So in this case, I'd be looking at the molecule this way. These 2 hydrogens and the carbon are in the plane of the chalkboard. This one's behind the plane of the chalkboard, and this one here is out in front of the plane of the chalkboard. I'm not too good at making nice drawings, but there you'll see drawings in books, for example, where they're done fairly nicely. And this is to indicate that it really is a 3-dimensional structure. That 3-dimensional structure has a number of implications.
So I cut out a portion here. So far what we saw John explain is how to translate from one type of representation into another. And fast forwarding a little bit, you're going to see what he's talking about next.
One end of the molecule is constantly rotating with respect to the other. And that becomes important if, for example, we substituted for one of the hydrogen atoms some other atom, and then essentially all of these kinds of structures would be equivalent to each other that correspond to rotation around this bond. And what that means is that if we made the molecule with, let's say this is a chlorine atom, and we made that structure, that would correspond to this kind of arrangement of the atoms. But we could just as well rotate the chlorine around this way, and then that would correspond to this. And so those 2 look different on the chalkboard or on paper, but they're the same structure because of this rotation around the single bond.
All right, so now he's connected this translation to a concept which is related to bond rotation, and that is something that is not visible in the Lewis structure. So you can have two Lewis structures that look different, but because you can translate it into this model, you can then eventually see that they're actually the same even though they look different. So switching back to my slides, this is an example of analytical sense-making skills. So students learn to make connections between different types of visual representations by actually pretty laboriously relating them to the concepts they show. Like this takes up, some portion of time. So he goes into verbal explanations about how these relationships can be explained by relating them to concepts. Another example is translating between these types of representations. They actually look very different. They show very different information about the molecule, but we can map like a triple bond here to a region of high electron density. So we're, again, explaining relationships here by referring to concepts. A second type of visual skill that is, in my mind, qualitatively different are what I call perceptual intuitions. So I want to show you again an example of this, going back to John's lecture for a second.
If we look at that structure, you have to think of this structure.
So I have another video from this is first week of an organic chemistry lecture where the instructor also talks about something that I think matches what I mean by perceptual intuitions.
And what I want you to do right away, and as early as you can in this course, is make sure that when you look at a structure like this, in your head, you're visualizing a pretty 3D structure like that. There are a couple of ways to get yourself to that level. One is to look at a lot of computer-generated structures, either online or in a textbook using some software, or using a model kit yourself to build these structures and actually holding them in front of you. One way or another, whether it's through the textbook images, some websites, or some model kits, I need you to know what these molecular structures actually look like.
Okay, so what we see here is there is some emphasis in students having to be able to just quickly move, even just mentally, between different types of visual representations. Like when you look at this Lewis structure, you have to think of this 3D structure, and we want you to be so good at this, so fluent in doing this, that like as soon as you see this one, you mentally visualize the other. I like to call that perceptual intuitions because I think it really gets at this idea, well, we want visuals to be intuitively accessible to the point that you actually see more than is actually being depicted. But it's also often referred to as perceptual fluency because it gives the idea that you're so fluent in a visual language as if you're fluent in like a second verbal language. So without having to laboriously translate or explain these translations, you can just do it. It's automatic. And chemistry is actually an interesting domain in this regard because in contrast to many other domains, educators seem to be really aware that this is an important competence. For example, Anderson and Bodner had an article where they investigated why it is that students who are really successful in general chemistry courses then suddenly tend to fail when they get to organic chemistry. And one of the reasons that they identified is that students had trouble interpreting line structures, so Lewis structures, and also skeleton drawings, not because they were unable to do so, but because it took conscious thought and effort to interpret these structures correctly. So in essence, students who have just analytical skills, like they can translate kind of laboriously and by like going through conceptual explanations, yeah, then they can translate between these, but they don't have the perceptual intuitions that allow them to do so fluently and automatically. So what I found is that students acquire these perceptual intuitions by getting used to, through exposure to many examples, and that is what you saw in the second person's lecture. He was talking about, well, you want to get you want to look at many websites. Like, you didn't give very specific instructions on how to get there, right? That's a problem that I'm hoping to address. But like, you need exposure to many examples so you can eventually pick up on perceptual cues like the dimensionality of molecules to give you an intuitive sense of, well, these probably show the same molecule. So that's what I mean by perceptual intuitions. Now, I think it's pretty clear that when we're out in the real world, these are actually related, right? We're using both analytical and intuitive skills together. For example, we might see a red light and automatically stop, so that's the intuition part. But then we might wonder whether we can whether it's allowed to take a right turn even when it's red. So that's the more analytical part. Hopefully you don't do that automatically, right? But distinguishing these two, even if they're related, distinguishing these two types of visual skills, I think might make sense because they're learned by qualitatively different processes, and for that reason they are best learned through qualitatively different types of interventions. So these sense-making skills require explicit and verbal explanation-based reasoning processes, right? You saw John going into these in-depth explanations of how the bond rotation explains that the two Lewis structures showed the same molecule. And therefore, instructional interventions that support these skills engage students in verbal explanations. By contrast, the perceptual intuitions, they're acquired via inductive, nonverbal pattern recognition processes, so learning to pick up on perceptual cues. For that reason, they don't require verbal explanations. Pattern recognition processes might actually be impeded by having students explain. There's some research about that, but at the very least, verbal explanations are not necessary. Verbal explanations take time, so they might actually take time away that you could invest in getting exposure to many different examples. So for that reason, Phil Kalman is actually a person who's done a lot of research on this, and yeah, you asked me about it. So he advocates for exposing students to many different visual representations and have students sort or categorize them just without verbally explaining why they show the same molecule or not, just to get students exposure to many different examples. So then, the next question is, how do we design educational technologies that can support students in acquiring these different types of visual skills? So what I do when I design educational technologies is I like to work really closely with educators in the domain to really ground the design of the technologies and how instructors use visuals in their teaching, and also to make sure students would actually solve problems that are similar to what they would normally do in problem-solving exercises within their class. And then I conduct user studies with students to make sure the technology aligns with how they think about the visuals and about the concepts, and also with like the difficulty level that they need support for. And going through these processes, I didn't want to focus on that today, but I just wanted to show you what the activities look like that I've developed in my lab for supporting sense-making and perceptual intuitions. So this is an example from ChemTutor where students learn about bonding concepts and are supported in making sense of connections between, in this case, space-filling models and Lewis structures. So we give them an interactive component where they construct the same molecule. We don't even tell them what the molecule is. They're supposed to figure that out. And then they get feedback from the system to, if they, in this case, don't pair up the electrons, they get feedback from the system to fix that so that they kind of, get support only when they need it. To learn to translate between these different visual representations, and then we have reflection prompts for them to think about, well, what is it that one representation shows that the other one doesn't? Mike and I talked earlier about how I think these fill-in-the-gap self-explanation prompts are probably not ideal, If you have questions about that, I'm happy to talk about it. But that's the way we implemented sense-making support in the studies that I'm going to talk about. The prompts themselves are actually based on what they're based on this expert-novice comparison that I was talking about earlier, where we had students kind of explain how they think about visuals, and we had chemistry PhD students explain how they think about them, so that we could prompt students to talk about them in ways that the experts did but the students didn't. And we also made sure that the wording of the prompts as well as the feedback, so students actually get feedback on, when they fill in the blank here and they put in the wrong answer, they get feedback on that. And we made sure that the wording reflected ways in which chemistry PhD students and undergraduate students were thinking and talking about the visuals. But yeah, the idea behind these problems is to get students to reflect on similarities and differences between the different types of visual representations. What is it that one shows or emphasizes that the other one doesn't show or doesn't emphasize? And essentially that should answer the question, why do we need both, right? So the perceptual induction activities are very different. Here we give students one visual and we ask them to select one out of many other visuals that show the same molecule, and they get immediate feedback on this without any explanation. We basically tell them, solve these problems as fast as you can. Don't be afraid of making a mistake. Treat them like a game. Just follow your intuitions. We're trying to build your intuitions. And then we give them many of these in a row. They get only correctness feedback without explanation, and we tell them, yeah, try again. We try to expose them to as many different examples as we can, while the choice options are designed so that they contrast visual features that we want students to start to pick up on. So for example, here you see this one has 4 things attached to it, so does this one, so does that one. Now that one has a similar structure too, except that there's a missing thing here, which is a lone electron pair, which the students may or may not know. So we kind of set up the examples here so that students' visual attention is being drawn to the relevant features. We also did eye tracking studies to help us confirm that, but that's basically how they're designed. There we go. Any questions so far? Yeah?
So, as you were moving through the slides from the beginning to the one previous to this, we caught real quick snippets of the feedback that students are getting, both for the Lewis structure that was drawn at the beginning, and then the one here, this one as well.
Yeah.
So the feedback seems to be very focused on getting them to analytically produce the correct diagrams without linking it to the represented world. So the feedback that says you're close, remember that lone electrons need to be paired. So that's just an algorithm that I could use to generate this structure, but doesn't tell them why they're paired together, because there's a reason that we draw them this way. Do they ever get feedback that helps them understand why the representation has its particular shape?
Well, not in this problem. I think towards the beginning, when we first introduced Lewis structures, they do get some information about why it is that way. We don't go into very much detail in that. But yeah, that would be, so before they receive problems where they have to make connections between 2 different types of representations, they have some problems where it's just one representation at a time. And that is where we introduce the notational system that each visual is using. Now, I actually do not think we actually explained to them why it's showing the electrons as paired. So I guess my answer is kind of yes and no. Yeah.
A quick aside. Has any student ever seen both of those pieces of feedback, the same student, because they directly contradict one another? Because
Which pieces of feedback?
the feedback on the first slide says you're wrong. Remember that the electrons should all be spaced as evenly as possible, and that contradicts this feedback, which says pair them together.
Well, but the other slide that you're talking about was just the Lewis structure of one atom. So that, yeah. So yes, students have probably seen both, but they're part of different units.
Okay.
One is on atomic structure, and this one is about bonding.
Okay.
But yeah, it's never occurred to me actually that that's a contradiction.
As somebody who teaches chemistry, they catch these things all the time and complain about them loudly.
What would you respond?
They're that way for different reasons.
Okay. All right, I might ask you more about that later.
Sure.
Yeah.
I had a quick question. So, how do you distinguish between the students when you're getting the perceptual activities who are just the button mashers, who are just, they're clicking until the green box shows up, versus the student who really is actually improving? Are you looking at things like latency to response, the number of false clicks before you get the correct answer, and like seeing does that decay over time?
Yes.
Like what kind of metrics are you looking for?
Well, I have many answers to this. First of all, if you really believe in the perceptual learning paradigm, you would think that they, just by being exposed to it, even if they don't try it very hard, they might still get something out of it. But I definitely look at error rates declining over time, also them becoming like more efficient with time. So yes, I do look at both.
Okay.
And then, you know, probably a related question as well, then what do you do with that information? I have one study that unfortunately happened during the time of the Super Bowl. So students were, you know, their instructor assigned this to them as a like homework assignment, and the deadline was on the night of the Super Bowl. And I saw very different results for students. Like, you know, I actually saw like half of the students worked on it during the Super Bowl, and I was puzzled why the data didn't show like high learning gains or lower learning gains than usual. And then it occurred to me that perhaps what if I filter out the students who were like looking at it at exactly the time of the Super Bowl, and you know, when I filtered those out, like the remaining students had much higher learning gains. So definitely think of those things when you're planning stuff. I mean, then, you know, the question is, how do I treat that data in my analyses? Like, if I identify students who just seem to be clicking, do I still include them, or do I exclude them?
Right.
Yeah. But yeah, I think it's pretty easy to identify students who seem to be gaming the system. Yeah. Right, should we go on? Where was I? Yes. So, now the big question is, how should we use these kinds of supports to help students learn about the domain knowledge? And really, the first question before that even is, do these sense-making activities and perceptual induction activities actually help students learn chemistry knowledge, right? That's the underlying assumption here, because if the argument is that, as I've argued, sense-making skills and perceptual intuitions are somewhat separate or distinguishable visual skills that play an important role in students' learning of chemistry, then I should actually see higher learning outcomes if students receive sense-making activities in addition to perceptual induction activities, and I should see these learning gains. I mean, it's interesting to see kind of as a like reality check, well, you know, students who receive sense-making activities should show improvements on a sense-making skills test. That is not as much what I'm interested in as, does it help them learn chemistry? So, I actually did a few of these experiments where I compared students who received sense-making activities, students who received perceptual induction activities, students who received both, compared to students who received what I like to call conventional activities. So conventional activities are where students receive only one visual at a time, and they don't receive any support to make sense of how different visuals connect to one another. So here's what I found. So here again you see a delayed post-test. This experiment was done as part of a introductory level chemistry course. Students who received only perceptual induction activities. This, by the way, is a chemistry knowledge test. So only perceptual induction activities, lower learning gains than the control condition. This is our control condition, so business as usual. Students who received only sense-making activities, no difference to the control condition. But students who received both in combination showed significantly higher learning outcomes than the control condition. And this was actually 3 experiments where I worked with first-year science majors learning about chemical bonding, and this experiment was done in the lab. I did another experiment where they learned with the same system about bonding, using it as a homework system. And then I also did an experiment using students from a non-science majors class where they learned about atomic structures. So, and I always found this pattern. Question?
Yeah, just in that condition where they learned both, what was the order of that? Did they learn all one and then all the other? Were they interspersed between each other?
I'll get into the sequence question on starting on the next slide, but in these experiments I always gave the sense-making activities before the perceptual induction activities. But they were about multiple topics. Do we have a whiteboard? Yeah. So say our curriculum covered 3 topics, right? And then for topic 1, they would receive some conventional activities first, then some sense-making activities, then some perceptual activities, and then we would repeat that for the next topic. Does that make sense?
Yep.
Also, the time on task was the same for all 4 conditions. So students who received, students in the control condition, they would receive conventional activities, more of them, so that it would equal the time that the other students would spend on all 3 types of activities. And students who received, say, only sense-making activities, they would receive some conventional activities and then sense-making activities that made up the same amount of time. So, and we established the timing based on pilot data. Yeah. Yeah.
So it strikes me that the direction of the effects on this bar chart are the same as the first bar chart that you showed us with prompts and no prompts and single versus multiple visuals. It's identical. Is there any similarity here between those 2 interventions?
The sense-making activities are very, very similar to what we did in the intervention condition of the first experiment where I showed the slide. But also, I mean, this bar is really not the same.
Not as low.
Yeah.
Yeah.
This bar is not the same condition at all as the lowest bar on the other slide.
Okay.
But I did a very similar experiment on fractions learning too, and there I found the exact same effect. Yeah. So I found this result very interesting because to some extent, I mean, that this condition is the best one is really what I had expected. So that's nice. But why is sense-making alone not good enough? And perceptual intuitions alone, why is that worse? That's something that I couldn't explain, and I was puzzled by it. So thinking about this, I could see two reasons for this. So it's clear that sense-making activities and perceptual induction activities interact in some way, so that only in combination they actually help students learn. So sense-making alone might not be good enough, because unless students translate their analytical knowledge into these perceptual intuitions, it might be similar to what Anderson and Bodner said, like they might know how to do it, but they might not be good enough to do it, so it's too laborious, it takes like conscious effort and time that doesn't actually help them learn chemistry, right? So it might be that, so that's one thing. That would explain why, that would explain why this bar isn't higher. It might also be that sense-making then helps students acquire the perceptual intuitions, because sense-making activities help students learn like which visual features are important, so that when they get to the perceptual intuition activities, they know what to look at, and that may help them learn the perceptual intuitions from those activities. It might also be that without having these sense-making skills, students cannot learn the perceptual intuitions, because unless they know what to pay attention to, they might even, just using trial and error, they might induce wrong connections, and that might actually hinder their learning, and that would explain why this bar is lower, right? Perceptual intuitions without having the sense-making skills doesn't even give you the right perceptual intuitions. So that's another possibility. It might also be that perceptual intuitions help students learn the sense-making skills, because if the argument is that perceptual intuitions decrease the cognitive, increase cognitive capacities that students have to engage in analytical thinking, then having like an intuitive sense of two visuals being the same showing the same molecule might help students then engage in like analytical explanations of why these two are the same molecules. So these different explanations have implications for how we should sequence the different types of activities, right? If I say, well, sense-making activities help students learn perceptual intuitions, then we should present sense-making activities before the perceptual activities. If we say the perceptual intuitions help students learn sense-making skills, then we should present them in this order. So obviously what I did was I did another experiment where I compared exactly these two sequences, and I did this again on 3 different experiments with students taken from different types of chemistry courses, learning about different types of either atomic structure or chemical bonding topics. And what I found was that the effect actually depended on students' prior chemistry knowledge. For students who had low prior chemistry knowledge about the topic that they were learning about in the given experiment, they benefit more from receiving the perceptual activities first. Students with high prior knowledge, for them the effect was flipped. They benefited more from receiving the sense-making activities first. And again, I found this across 3 different experiments with different students and different topics. The more interesting thing about this was, I think, an analysis about how these effects came about. So looking back at, these are the different hypotheses that I had, right? Either sense-making helps students learn perceptual intuitions, or perceptual intuitions help students learn about the sense-making activities. So what I did was I conducted causal path analysis where I looked, I translated these basically in mediation hypotheses, and I'll unpack that on the next slide a little bit. Now, in these analyses, I actually treated prior chemistry knowledge as a continuous variable, but to explain it, it makes it easier if I just talk about students with low or high prior knowledge. So keep that in mind, that what I'm showing here is kind of a simplification of the analysis. So, looking at the students with high prior knowledge first, what I looked at was students who received sense-making problems. How does that affect their performance on the perceptual problems that they received next? So what I found was that students who received sense-making problems first, they made fewer errors on perceptual activities that they received next, compared to students who had not previously received the sense-making problems. And this reduction in error rates yielded higher learning outcomes on the post-test, while statistically accounting for their prior knowledge, right? Now I found a similar effect actually for students in the other conditions. So students who received perceptual activities first, they also showed lower error rates on the sense-making activities. And that also yielded higher learning outcomes on the delayed post-test. But the nice thing about causal path analysis is that it allows you to compare the strength of these effects in the model. And I found that this enhancement effect, right? So sense-making problems first, enhancing students' learning from these perceptual problems, because that is what this mechanism means. This path was actually stronger than the other path. So sense-making first helps students benefit more from the perceptual activities than the other way around. And that explained why students with high prior knowledge benefited more from receiving the sense-making activities first. Yep.
Did you look into brain? Because this is exactly what's happening in the brain when you're learning. So it totally makes sense. You have to have some prior knowledge to be able. The perceptual is much harder for students than the sense-making. Did you ever look at correlation? I come from kinesiology.
You mean like fMRI data or EEG?
Yeah.
No, I haven't.
Okay, because
that
would be quite interesting to do because.
Yeah, I don't have the skills to. Oops.
Oh.
Well, I'm giving everything away. Yeah, no, I have not looked at that. But yeah, it would be fascinating.
I may have missed this earlier. How did you distinguish the high prior knowledge students with from the low prior knowledge students?
Pre-test.
The pre-test? Oh,
Yeah. Okay, so looking at the low prior knowledge students, here we saw that students who receive the sense-making activities first, they actually make more errors on the perceptual activities. And the more errors they made, the lower their post-test. So this actually mediated learning gains on the post-test. The same was true for the other conditions. So perceptual activities first increases students' errors on subsequent sense-making activities, and that also yields lower post-test scores. Now, comparing the strength of these two mechanisms again, this first, I call this an interference effect. This first interference effect is stronger than the other one, and that explained why students in this condition show low prior knowledge students had benefited more from receiving the perceptual problems first. So this is interesting for two reasons. First of all, students with high prior knowledge, both effects are true, right? So sense-making skills seem to help them learn perceptual intuitions, but also perceptual intuitions help them learn sense-making skills. But the first effect is stronger, so sense-making first enhances their learning from perceptual activities more so than the other way around, and that is why they benefit from this sequence. So that's all fine. But for the low prior knowledge students, it's actually not an enhancement effect. It's less interference that accounts for the benefit from this condition. So it's not that one enhances their learning from the other. It's that one interferes with their learning from the other to a lesser extent, and that is why it seems to be beneficial. But then we also have to ask ourselves, well, do they really learn? Do they really benefit from this combination, or is it too much for them? So I think the interference effect can be explained by just task switching costs. So when you switch from one type of activity to another type of activity, and these are, really engaging them in different learning processes, you have to mentally switch gears, and that always comes at a cost. And in this case, for the students with high prior knowledge, it doesn't hurt them. For students with low prior knowledge, it seems to hurt them, but this sequence seems to hurt them less. Now, my goal is not to have an intervention that hurts students less than another, right? So this is perhaps not an ideal setup for the students, but it's interesting because, so first of all, I've identified 4 mechanisms. One is conceptual enhancement, one is perceptual enhancement, then conceptual interference, and one is perceptual interference. Now, probably all of these happen at the same time, but they're moderated in strength by students' prior knowledge. So that is where I'm currently at in my research, and I feel like there are a lot of follow-up questions that we need to ask. So first of all, for the students with low prior knowledge, is the combination actually the best? In the experiments that I've done so far, it was always rather short interventions where students received the sense-making activities and the perceptual induction activities for a rather short sequence of topics. But what if we look at that over the course of like a whole semester? So what I'm currently doing is I'm looking at how these interactions between the sense-making activities and the perceptual induction activities unfold over time, over the course of a 10-week instructional unit where students cover a broader range of topics. And what I hope to see is at what point in time sense-making activities are effective, and when do the perceptual activities become effective, because it seems like students with low prior knowledge may not actually benefit from receiving both of them together. It seems to be like too much for them because of these costs of switching between different types of activities. So we're still collecting data on this experiment, but what I'm seeing so far is that students at the beginning of, well, when they're first introduced to a pair of visual representations, in the first week or so, they benefit most from receiving just conventional activities that introduce them to only one visual at a time. And then the second week that they're using these two types of visuals, the most effective condition is the one that gives them sense-making activities only. And then only starting in week 3, the perceptual activities start to become effective. So that, in my mind, really maps onto these effects. So students with high prior knowledge, they seem to benefit from doing sense-making activities first, followed by perceptual induction activities, because one enhances the benefit from the other. Now, these students were in this condition, like, even though on the surface it looks like this is an effective sequence for students with low prior knowledge, it may actually not be. And that is what I'm trying to uncover in this new experiment, where I can look at these effects unfolding over a longer period of time. So that's one of the things that I'm currently focusing on. And then building on that, I plan to create adaptive sequences that don't just optimize this over the course of multiple weeks using the same sequence for all students, but I would expect that students learn at different rates. So ideally, they would probably benefit from different types of activities that match their individual learning rate of these skills. Another thing is, what is really this prior knowledge? It's very, very difficult to separate content knowledge from knowledge about the visual representations because of what I showed on my first slides. Like, we're using the visuals to help students learn about the content knowledge, so presumably they're learning both at the same time. So what I'm also interested in is, like, when does that perceptual enhancement mechanism, so perceptual intuitions helping students learn about the chemistry knowledge, when does that start to prevail over these interference mechanisms that I discovered? So in comparison to that perceptual interference mechanism, where like students may have perceptual intuitions that take away their ability to learn new knowledge. So I think the reason why these perceptual interference mechanisms might occur, so perceptual intuitions increasing students' errors on subsequent sense-making activities that interfere with their learning, right? I think that might be because they give students a false sense of being familiar with the domain or being familiar with the visual representations. So students may feel like, oh yeah, I know what that means. They stop thinking. So like we stop at red and we don't even question whether, have any of you ever stopped at red and then at some point you realized, oh yeah, the light is like flashing red, it's like, you know, it's actually not working. That happens, right? Or like we take emoticons and like they're really intuitive, but I don't know, I don't have the like visual literacy really to interpret text messages that are only composed of emoticons, which some people do. Yeah, you might think it's intuitive, but you stop questioning yourself. So I think that might be one reason why perceptual intuitions can interfere with students' learning. So one project that I'm currently working on is how can we assess students' perceptual intuitions? The difficulty in assessing perceptual intuitions is that they're not necessarily verbally accessible. Normally when we develop methods to assess knowledge, we really rely on verbalization. Like we do think alouds or we do interviews. And for these types of perceptual intuitions, that's not necessarily the best case. Now we can use eye tracking to see what visual features people pay attention to, but even eye tracking data is very difficult to interpret because just from knowing what somebody's looking at, I don't necessarily know what meaning they perceive in that visual feature. And also, eye tracking is, at least at the moment, not scalable, so it's difficult to take it into a classroom. What we're trying to do here is we give students triplet comparison tasks that just ask them, well, which visual is more similar to the top one? And we give them many of these tasks in a row, and through that we can see which perceptual features, like the number of lines or the number of dots or the number of C's, which of these drive students' perception of similarity between molecules. And in a first study of this, we gave these tasks to a bunch of chemistry students, and then we can kind of map out the visual features that drive students' perception of similarity. So in this case, I know this is way too small to read, but in this case we just mapped out the molecules represented as Lewis structures on 2 dimensions, and then had a chemist interpret these groupings for us, and they actually make up meaningful chemical groups. So it seems like even if we just take the 2 most important visual features that drive students' perceptions of similarity, we can kind of reconstruct meaningful chemical groups. And we did a similar analysis of students being presented with ball and stick models, and what that allows us to do is to, again, identify the visual features that they most pay attention to without using eye tracking or any of that, and without asking them to identify those. And then what we can do is we can develop ways to challenge those perceptual intuitions if, for example, they're incorrect. Like students often pay attention more to surface features than meaningful visual features because they haven't learned which features are meaningful, right? So that makes sense. And then we developed a machine learning model that learns the perceptual features in a similar way as human students would do. And then we kind of reverse engineered training sequences for the perceptual induction activities that would challenge those incorrect perceptual intuitions and train students to develop correct perceptual intuitions. So we had a machine learning model learn with all possible different sequences in which we could present visual stimuli to students, and then select the optimal sequence that led to the highest learning gains for the machine learning model. And then we did a human experiment where we tested whether the humans also learned better with that optimal training sequence. So in this experiment we compared 3 conditions. So students learning with the machine optimal sequence, another group of students learning with a sequence generated by a human expert, who in that case was actually me. And then other students learning with a random sequence, so just visual stimuli presented in a random sequence. And here's what we found. So on the pretest, no differences. During training, students who were learning with the machine-generated sequence actually had significantly lower accuracy than the other conditions, but then they outperformed the other conditions on the post-test. So what we think happened here is that the machine learning model kind of identified a desirable difficulty level for students learning from these perceptual activities. And really, what is that if it's not challenging students' existing perceptual intuitions, whether they're correct or incorrect? And then that resulted in a learning gain compared to the other conditions. And I mean, I'm not really offended that the machine is outperforming me. I'm a little bit offended that my sequence did not outperform a random sequence, because I really think I selected visuals in a sequence that would draw their attention to meaningful, I'm a psychologist after all, so I thought I could do this. But I'm no better than random. Now we all know probably that random is actually a high bar to meet, but I thought I would be a little bit better than random. Turns out I'm not. So I found that very revealing. But yeah, so I hope that we can expand this research to identify also, you know, why, like what about this sequence made it effective. So we're still analyzing the data from that regard too. So that's an experiment that we're currently conducting. A final thing that I'm interested in is, you know, students come in with perceptual intuitions. That's pretty clear. Like we all have some intuitions about like what this shows, even if we've never seen this before. One might be like, actually we talked about this earlier. One might be, well, if this is a bond, then a bond is a stick. A bond is a physical thing. That's a misconception that students often have about bonding that probably stems from these physical models. But I mean, we can't really prevent them in developing intuitions like this. The question is, what do we do with this? So one question that I'm interested in is how we can identify and how can we then build on students' correct perceptual intuitions. So in this project, I'm looking at differences between physical and virtual models that might activate different types of perceptual intuitions. So if we take, for example, this physical model, right? So the way we build a bond is like we take the stick and we push these two spheres together, and then pushing them together, and then at some point I feel a resistance when I can't push any further, right? Now I want to show you just a 3-second video. Well, I think it's perhaps 12 seconds of how we build a bond stick model using a virtual tool. Alright, so you see that here we click, and then we drag, and then we release. Right? That's a very different movement than with the physical model. So my question in this project is, how do those interactions affect students' learning of chemistry concepts? So here's my hypothesis, and I'm in the process of conducting an experiment testing these. So if students learn about attractive and repulsive forces in covalent bonds, so when you have two atoms, at some point the positive nuclei of one atom starts attracting the negative electrons from the other atom, which results in these attractions, and then at some point when they get too close to one another, the two positive nuclei start repulsing one another, and that is why, you know, that bond like has a certain length, like doesn't get any closer than this, or is like an optimum of like the two electrons, well, no, the two atoms being at a certain distance from one another. So I think that when students learn about that concept, the physical model is actually more conducive to that, because you do this pushing and then there is a resistance, right? You can feel that, and that, even though that may not be conscious, it might make it more intuitive to learn about this concept. By contrast, if I learn about electronegativity in polar bonds, like if we say this is a chlorine atom, chlorine is highly electronegative, which means it has a tendency to attract electrons from other bonded atoms towards itself. So if we learn about that concept, the click and drag, you know, click here and then drag over and release, that might actually be more conducive to learning that concept than here when I'm pushing these together. Like I push, I don't drag. So my hypothesis is that when students use a virtual model to learn that concept, that leads to higher learning gains than using a physical model. And then just as a baseline, we also have some concepts that students learn about where we can't make this distinction between physical models or virtual models being more or less conducive to learning that. So we'll see what comes out of this experiment. I'm really curious, and Mike is actually on the advisory board for this grant. So yeah. Yeah, so that's another thing I'm interested in, how like the physical movements affect students' learning of perceptual intuitions, and how we can then use or hopefully build on the perceptual intuitions in a way that helps them rather than impedes their learning of sense-making skills. So yeah, that's what I'm hoping to do in my research, to like use theory about how people learn, to develop technology-based support for learning with visuals, and then use that to help them learn the chemistry concepts. Thanks.